Hello, in this video we're going to look at the inversion formula for the characteristic function. And what that means is if you know the characteristic function, how do you get back the PDF? If you know the PDF, then there's a specific formula to find the characteristic function, but there's a one-to-one connection. So if you know the characteristic function, you can get back the PDF. So let's let x be a random variable with PDF f, and it has a characteristic function phi of x. So if x is discrete, it's going to be one of these next two formulas. So if we only know that it's discrete, then this is the formula as t goes to infinity. But if we know that x is a lattice distribution, and we covered lattice distribution in the previous video, properties of the characteristic function, then it can be simplified. It was shown that, or noted that the characteristic function has period 2, and so it simplifies quite a bit. If it's continuous, then generically, and that's all we know, then this is the formula. As h goes to 0 and t goes to infinity, it's this integral. So that you plug, we know the characteristic function and we get the PDF back. But if we know it's continuous and that the characteristic function, absolute value of the characteristic function is finite, then it simplifies to this function here. And so I was going to try to prove these, but I think I'm going to omit it because it kind of loses the beauty of what these really do. And so I'm going to give a couple examples, and then I'm going to commit to doing a series on the Fourier transform, which then covers these types of equations. But for this video, I'm going to omit it, and we're just going to use examples for these formulas. So let's let x be binomial, and we haven't shown this, but we're going to, in a later video, we're going to show that the characteristic function of a binomial is this equation, and where q is 1 minus p, and p is the probability of success. And we're going to use number 1 to find the PDF of x. And it should be noted that x is actually in the lattice distribution family, and so we could actually use I star or I prime, and I'm going to flash back to these. So we could use this simpler version to find the PDF, but we're going to use this more complicated equation just for illustrative purposes. So here's the equation without the limit sign. We'll do that at the end. And so we plug in our characteristic function and take it times this e. Well, this right here use the binomial formula for that, and that's what this is, where this is here, and the q comes from that, of course, and then you sum from 0 to n because that's an n. This piece stays the same. Now it's a linear operator, so we can take it in, but we have to keep everything over here that has a t, because that's then it's not a constant and can't be taken out front. So that's a constant. The e here, we'll have to pull in the t, and that's why we get this r minus x. The p to the r comes out, q comes out, and this e and that e combine to be this. Now, we do have one thing here though. When r goes from 0 to n, r can be x, and if that's the case, we have to treat it differently. So we're going to break this into two pieces where r goes from 0 to n and r is not equal to x, and then when r equals x. And that's what this next piece is. So I ran out of room. So this is the where r is not equal to x, and when r is x, so there's only one piece, there's no summation sign because it's just one term, then this is 0 and it drops out to 1. And then otherwise it's the same as this. Now, to integrate this here, oh, and also notice that I divided by and then multiplied by this quantity, so it's multiplying by 1. So this is actually the same. And I did that when you use a U substitution, then these pieces come in handy. Then you take the limits of integration, you plug in t, and then subtract t, and that's where this is. So that is this piece, and then here you just get 2t when you integrate that piece. So then the 2t's cancel and we're just left with this. And then, you know, this is all the same. The bottom is not. So when you do this here, so this is would be cosine plus the sine, and this is cosine plus the sine or minus the sine, but then it becomes, you know, the cosines cancel and the sine combines into this. It actually is 2i of them. So then that's where this 2 and the I kind of cancel with that, and that's where they're not here. And we're just left with this. Now, if we let t go to infinity, here it's just a constant, so it stays the same. But this is bounded between -1 and 1, and this piece goes to infinity, so the whole thing goes to 0. So this goes away, leaving just this piece. So that tells us f of x is equal to this. And we know that that's the PDF of a binomial distribution. So let's do one more. Let's let n or x be standard normal, and it can be shown that the characteristic function is this. And if you take the modulus of the characteristic function, you get this, because this is always positive. And then if you integrate this, you know, that is looks like a standard normal equation, and we know that it integrates, it's finite. So we know this. So we're going to use 2 prime to find the PDF of x. So we plug in our, you know, this is the formula. We plug in our information for the characteristic function, which is this, and we combine those to this. Now we complete the square on the top part, so we have to add and subtract this amount. And notice that we're actually, this is the minus and that's the plus, and we do that, and then this is constant in regards to the t world, so it can actually be taken out front. That's what this piece is. And then we go ahead and complete the square on the top, and the 2 pi we break into the square root of 2 pi, square root of 2 pi. Well, this becomes a standard normal. The variable is t, and so it's minus the negative of that, and then anyway, that is 1. So what's left over is this piece, which is this. So this is the PDF of a standard normal, and we know that by definition. And there's only one other point that I'd like to show in this video, and I'm going to call it the uniqueness theorem, and that there is a one-to-one correspondence between the characteristic function and the PDF of a random variable. The proof is sort of by the inversion formulas. You can show it that way. If you know the PDF, you calculate the characteristic function, but that characteristic function, you get the PDF back using those inversion formulas. So there is a one-to-one correspondence. And so if you derive the characteristic function for a random variable and that characteristic function equals a known characteristic function, then then they have the same PDF, or probability density function. And so that's a trick that we use over and over and over. And actually in the next video, or maybe the one after that, we'll prove the central limit theorem using moment generating functions. Anyway, so that's all I have for today on the inversion formula for the characteristic function. Hopefully you liked it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.